Okay, so today I want to kind of subdivide our lecture into two parts. I've updated the resources section inside of the Discord to include a rough cut of the textbook so that you can go ahead and start reading at least a digital copy of it. And so here I'm going to take a small segment of today to talk a little bit about software engineering as it's discussed in the textbook for chapter 1. This isn't going to be a very long slide deck, but it's going to establish some of the kind of foundations that we're going to lean on in terms of how to think about software engineering and really kind of define what software engineering is. After we're done the slide deck, which I'm hoping might take, I don't know, we'll see how long it takes. Not a whole lot of slides. And I think a lot of this will be self-evident as we walk through the slides. And the second part of today, after we're done with the chapter 1 slide deck, is I want you all to kind of group into your pods. I'll leave it to you if you have team members that or if you have peers that you already have worked with to kind of pair off with. And outside of that, then we'll just go ahead and make sure that every pod has 3. So those are the two quick kinds of goals that I have for today. Once I have the pods set up and once I know how many pods we have, what I'm going to do then is I'm going to do the assignments of what technology each pod is going to have. And so this will be assigned through Discord. So it's very important that everyone is on the Discord server, because that's where a lot of the resources and that's where a lot of outside of lecture communication is going to occur at. Okay, so is there any questions before I start at least the lecture component of today's class? Excellent. Okay, so we're going to go through my very ugly slides. And hopefully we can get through this relatively quickly. Okay, so this is going to be really focusing on chapter 1, where we're going to define what is software engineering. And so here, in order to try to understand what software engineering is, and just so you know, before I start the lecture, I will share these slides with you. And also, even though this isn't an online course, I'm still using Zoom to record everything I'm saying so that I can then share these videos with you. So there is a videos channel, someone asked about that. I will upload that probably once a week at the end of the week so that you have this for resources so that we can really kind of focus in on having a class discussion and kind of understand the concepts without you having to put pen to paper. Now, I understand putting pen to paper is one way that you can learn. So if that's a learning mechanism for you, by all means do that. I know a learning mechanism for myself is to take notes. But if you miss anything, you'll still have the lecture slides and the lecture, well, our interactions that we have. Okay, with that said, let's open up by trying to define what is software engineering. And so let's give the actual definition from the textbook that we're using. So software engineering is the systematic application of scientific methods and empirical evidence to develop efficient, cost-effective solutions to practical software problems. Okay, let's unpack that a little bit. When we say scientific methods, what do we mean by that? Well, scientific methods means that we kind of involve some kind of discovery process to identify new knowledge through observation, experimentation, and empirical evidence. So here, the goal is to apply an engineering approach towards software development. So here we want to contrast what is software development and how do we elevate that to software engineering. Up to this point, you've been doing software development. So with an engineering approach, what we're looking to do is apply the scientific knowledge pragmatically to solve real-world problems, things that we can actually apply and build that we deliver to clients, that we deliver into the world. And so why does this matter? Well, adopting these engineering approach helps in managing the complexity of software systems, ensuring sustainability, and promoting continuous learning to improve and refine systems. So let's talk about the exploratory nature of software development, because we can really kind of contrast this. We can compare this towards the exploratory nature of scientific research in general. Think about what you do in scientific research and think about what it was like even in Java 1 when you were poking around and playing around to see what works to build an application where you might implement it, you have an intuition, you have an idea of what might happen, but then you can inspect the state at any time, right? You can do a print statement, you can use debugging tools, and then you're learning, you're watching, you're adapting your software until it accomplishes the task you need it to do. Do you kind of recall that kind of like give and take experience early on, probably even now, right? Probably when you have an idea and when you're initially prototyping, you're throwing like mud at the wall and you see what sticks. So that kind of concept is one that drives how we can constantly improve and build out from like a minimal viable product to something that is a very robust software system. So the key here then for both approaches, whether it's a scientific research or whether it's software development, is that learning is going to be one of these core skills. And so we constantly have to not only adapt to kind of understand the problem at hand that we're trying to solve, but also what tools are available to us to solve this problem. Again, we don't want to put ourselves in a position to reinvent the wheel. If there are third-party tools, we want to adopt them and bring them into our workflow. And for this class, that includes AI tools. Perhaps, unlike maybe some of your other classes, I will indeed encourage you to use AI tools to be able to produce software much more rapidly and prototype to get builds or applications that work. Because at the end of the day, this class is more about building deliverables, right? And so you want to take advantage of all of your assets, resources, and tools in order to afford you that. So again, the goal then here is to explore and iterate on ideas through small, flexible experiments to discover effective solutions and refine them over time. So then let's talk about, so if there's a discovery-like model that goes into software development that's akin to scientific research, let's see how we can apply the scientific method towards software. And so what are the steps of the scientific method? We can break them down into 4 different steps. You characterize, hypothesize, predict, and experiment. So you characterize by first observing and analyzing the current state of the software system. You can identify the key features, the issues, the areas that need to be improved. Then you create an hypothesis where you formulate some theory or potential solution that explains the observations, what the issues are, what the deficiencies in the software system is, or how you have to grow it to meet the needs of your clients or whatever the problem at hand is. Then you have to predict. Here, once you've formulated where the deficiency is, you have to determine what a solution is. You'll develop a prediction about how the software will behave as you attempt to improve it, and you'll try to also predict what cascading problems, what after effects might occur by making these additions. Because in that way, you can try to predict what will go wrong by expanding out your software system. And then finally, we'll experiment. You'll implement on those hypotheses through coding, through testing, through simulations. And so simulations, we could talk about things that happen on the front end and interactions that happen on the back end, and actually the middle ground, how the front end and the back end connect. Like all of these are parts of the same problem that you're developing. I have one other chair that someone can... Okay, well, I'll just leave it there. Anyway, the importance here is that you want to organize your software development around these steps to reduce the likelihood of incorrect conclusions. So again, you're trying to think of how can you build out your application as if you were scientists in the field making predictions that create predictable outcomes. So let's talk about the role of empiricism in software engineering. First, let's define what it means to have empiricism. Is this a term that most people have heard before? Well, that's why I have a slide that defines it. So here, this is the mindset of making decisions based on observed evidence and data. So we're going to be data-driven. We're going to be evidence-driven when we make our decisions. That means we're not going to just rely on intuition, the first thing that comes to mind, or untested theories. So this is why experimentation is such a big part of building robust software systems. This is why test-driven implementation is going to be something that's going to be highly praised inside of software engineering, much like it would be in traditional engineering. So some of the practical applications on how we can apply empiricism towards software engineering is we do iterative learning. So we're going to continuously refine software through repeated cycles, where each iteration builds on evidence, something that we know, and then we can add a little bit more. So we can control the amount of variability, and we're constantly expanding the complexity of our software system in small modular chunks that we test and validate first. Then we do our experimentation, where we can regularly test and validate the hypotheses to ensure that the development is guided by proven, validated insights. Validate is the key word. Validation happens through testing. And then finally, we make those data-driven decisions, where we prioritize decisions based on the results that we get back, and that's however we define those measures to be. And we ensure that the direction of the project is supported by that evidence. And of course, the goal of this, the outcome that we intend, is to have that improved reliability of our software system at any stage while it's being implemented, from an early stage towards the more complex stages, provided we follow this as a set of principles. So let's talk about then what it means to have an engineering mindset. An engineering mindset usually consists of having this attitude towards continuous learning and adaptation or adaptation. So here, the key competency here is, for continuous learning to be a successful software engineer, you need to know or be ready to learn new technologies and methodologies and techniques, because your project requirements are going to evolve throughout the life cycle of the application. So the things you might need to know early on when you first start the project might be completely different than the things you end up having to learn towards the tail end of the project. And the set of tools might change too, from early prototyping to when you're ready to go to production and deployment. And so you have to be prepared to learn all those tools and keep readapting and keep modifying your software under the changing conditions of your work environment. And again, the applications here, the way that we can actually make use of this is through experimentation. So regularly experiment with new ideas and approaches, try using different tools to see how they work, try different approaches to see, like in a tiny toy-like way, to see and mock how well it's going to work, so that you can try to scale up the solution that works best for you. Get feedback, right? So when you experiment, the idea is that you're attempting to test something, and then you want to get feedback back. And so when you get feedback, get it from stakeholders as well. So we're going to learn more about these agile development cycles that brings all stakeholders to the table, and they'll be part of like this iterative experimental cycle to see what works and what doesn't work. This is very unlike how traditional engineering is going to work. We'll talk more about that in another slide deck when we talk about the waterfall approach, which might be the approach you would take to build a bridge versus building software applications, which works more like a wheel or a cycle. Okay, so how can we manage the complexity of our software systems? Because up till now, you've probably worked on relatively small software systems. And so when you start talking about large scale systems where you might have dozens of developers working on them in tandem, how do we manage that? And so here, I'm going to introduce the term CLAMS. CLAMS stands for Cohesion, Loose Coupling, Abstraction, Modularity, and Separation of Concerns. So let's kind of step through those just line by line. We're going to see how CLAMS is going to aid us in being able to all work together. Has anyone heard of CLAMS, by the way? Okay, so let's talk about this. So cohesion, what does cohesion mean? Cohesion is where we can design each module with a single well-defined responsibility, which improves the clarity, the reliability, and ease of maintenance on our software as a whole. Loose coupling. What does it mean to have loose coupling? This is where we can design modules that interact with one another with minimal dependencies. This makes the system much more flexible and allows for easier updates, testing, and scaling. So we don't want when we create modules, we don't want them to be cross-dependent on one another. We want them to be as autonomous and self-contained as possible. And again, cohesion is that each, if I didn't give you a follow-up description on that, that's where we want each of our packages to be well-defined. And so we identify a group of roles, a group of logics, a group of objects, software objects that make sense to go together, and we package them up. Well, that's going to be modularity, but we want all of our packages to be cohesive, where, like, for instance, if I'm building a set of tools that relate to, say, for instance, string modifications, I shouldn't put something that's unrelated to string modification, like something maybe for casting integers or something, right? That breaks the cohesion of that module, of that package. Abstraction, we talked probably already a lot about abstraction when you're talking about Java, and the core concept is going to remain similar. Here, this is where we simplify complex systems by focusing more on their essential features and behavior while hiding unnecessary details to reduce the cognitive load on developers. So, for instance, when we were first learning how to do Java and we went to print something to the terminal, we didn't need to know anything about how the printing to the terminal worked, right? We would just use system.out.print, and that was abstracted away from us. And so each pod, and the way that this is going to relate in this class, each pod will worry about the internal mechanisms and implementations for whatever code they're going to deliver, but then you would release an API, a set of function or procedure calls that can be called upon your package or your modules, and then the rest of the class only needs to know how to make calls onto your software package. Very similar to how you already read other API documentation to build out software. Modularity, this is where we break down the software system into small independent modules or components to simplify development. So clearly, you're already familiar with how modularity works. It's a core principle in object-oriented design. It's a core principle in API. Just in modern computer science and modern software development, this is a big component of it. So every time we would import a package that would effectively have some kind of cohesive set of responsibilities, like whether it was like the integer package or whether it was the utility package, right? They all had, you could kind of guess what functionality it would have even without reading the documentation. And then finally, our separation of concerns. This is where we can divide the program into distinct sections where each section handles a specific aspect of the feature of our software, making it easy to manage and update. Okay, so if you haven't heard of CLAMS, probably the concepts that drive it is pretty intuitive, wouldn't you say? On how you can start to discretize. If you think of a large application as like this continuous system, then your role as a software engineering is to find ways to discretize it and chunk it into smaller, simpler parts, and then figure out how to get those parts to fit together. It's like taking a whole image and turning it into a jigsaw puzzle so that each person can make a piece of that jigsaw puzzle. Okay, so let's talk about how we can then organize the organization for software development so that we can have this kind of coherent approach towards development. So the core idea here is that we want to take these and combine the learning. We talked about how important it is to have this ongoing learning and how we can manage the complexity. So we had all these strategies that we just laid bare, such as CLAMS, how important it is to do this iterative experimental cycle and then get feedback. And we want to develop that into a cohesive plan. So this is what we will call a structured progress, where we can apply the integrated techniques here, along with systematically throughout the our development cycle systematically. So how do we do that? Well, first we would define clear phases during our development cycles. And here we would do stages such as our planning phase, our design phase, our implementation phase, our testing phase, and our deployment phase. And this can be an iterative cycle, right? So we maybe might start on an MVP where you're only trying to execute tasks and create a simple module that will be part of the larger application. Each person could do this in isolation, and then you can start merging these modules together and do this process again and again until you have built out your complete application. We want to set milestones. This is going to identify key points within each phase to assess the progress and ensure that the project is on track and working as per expected. Don't ever do a lot of implementation without checking and testing and verifying first before you deliver and move on to the next phase. You need to create deliverables. It's not enough to just be able to say, I'm going to work on this abstract thing and then move on to this other abstract thing. When you define your milestones and make it something that you can deliver towards other teams or deliver to either internally to your team or externally to the other teams. So you have to understand what your output's going to be between each milestone. And then once you have deliverables and once you have these milestones, then you want to do these iterative reviews where you can go ahead and regularly assess and refine this process and align this with the project goals and make sure everyone's on board and understands how this works and get feedback in case you need to improve it. And this feedback can happen in one of two ways. Internally, it might be optimizing the actual implementation of your module in terms of the internal mechanics, but it can also be externally as well, where you go ahead and you validate that what your module is delivering to the rest of the team is in line with what their expectations, that like when they go to make a function call, that they're getting all the data that they expect. And so like, for instance, just to give you a small example, and step away from the slides for a moment on like how important it is for teams to match up. Suppose you're working in a loosely typed language, such as like Python or such as JavaScript, and each team is expecting an ID of some sort to be able to access a piece of data. Well, it's important that all teams that are using that ID understand how that ID is going to be represented as. Is it a number? Is it a string? Is it an object that then has a string? Is it an object that then has a number? If one team treats it as one thing and another treats it as the other, that's going to induce a large amount of technical debt where you have to go back and refactor whatever that assumption was missed. And I only say that because I have seen teams in the professional landscape where that's actually happened. They made assumptions on something as simple as an ID, and then all of a sudden you had weeks more of work put on having to refactor what an ID was. Simple clarification added weeks more of implementation time. So that's why it's important to constantly be in communication so that you can catch those things earlier on and not later on. Okay, so let's talk about some common pitfalls that we might have encountered in software development and how each one of these principles will help us resolve them. So cohesion, for instance, can avoid, so there's a couple of things that we can avoid using these practices. There's something that's called scope creep, technical debt, and poor maintainability, right? These are the three things we're going to look at that we want to try to avoid by adhering to software engineering principles. So cohesion helps avoid scope creep because cohesion ensures that each module has a single well-defined responsibility. So by maintaining this high cohesion, it becomes easier to resist adding unrelated features to a module. Because you're not just trying to pack it in with all the features, you know where your boundary points are. How does cohesion help with technical debt? Well, high cohesion makes modules easier to understand and maintain, as each one does only one thing well. This clarity reduces the likelihood of introducing technical debt by overcomplicating or misusing a module. So technical debt is usually referred to when we have to go back and refactor our code base and change it after it's been implemented. This is something you want to try to avoid. Sometimes it's unavoidable. Sometimes we're going to break that. We'll talk about that in just a moment, though. Cohesion, how does that help with maintainability? Well, the cohesive modules are straightforward to test, debug, and update. When each module is focused on a single task, it reduces interdependencies and makes the system more maintainable over time. because then you can just do your unit testing on the modules. You can validate that it does everything it's supposed to and plug and play with it inside your greater application. Okay, looking at loose coupling. How does loose coupling help us avoid this scope creep? You know what? What might be fun is instead of reading it, to see if you can't predict it, and then we'll validate it. So let's not read this and let's just talk about it. How do you think loose coupling would avoid this idea of scope creep? And scope creep is where, as you're developing a part of your application, you just keep adding more and more features and complexity and
so if everything is dependent on each other, that makes it really easy to create work for yourself where you have to add more and more things because of these dependencies. But if everything is on independent things, then it's really easy to stop wherever you might not need that much.
That makes a lot of sense, right? How might loose coupling avoid technical debt? And so where technical debt is this idea where we're constantly having to refactor and remake things that we've already done. So the idea of loose coupling is we don't want too much. Well, does everyone understand what it means for code to be highly coupled? Yeah, and so think about if it's highly coupled, if you make a change to one thing that's highly coupled, then everything that's coupled to it has to be refactored and changed. So you can see that automatically brings in a lot of technical debt, right? Because now if I loosely coupled, I can change that one thing and nothing else is coupled to it, and then I'm done. I don't have to go backtrack and say, okay, what are all the things that depend on this one thing I just changed? Like, say, for instance, we loosely coupled the idea that we access an ID. Maybe instead of having an ID, just to give you a quick example, instead of having an ID variable directly embedded in all these objects, maybe we're using this function that has get ID. And then there's one thing that's dependent on providing that ID. That's a loose coupling, because now if everything was coupled to the concept of ID and we changed how we model our ID, we got to go through every module that has that ID and manually change it. That's a lot of technical debt. Whereas if they all depended on that one function, get ID, we don't have to change anything. How can it enhance maintainability, do you think?
It's the same thing that you can say to like.
Yeah, you see how a lot of this lines up, right? Okay, let's talk about avoiding pitfalls with abstraction. How do you suppose abstraction helps us avoid our scope creep?
You don't get into the weeds too much with how specifically to do something. You have a general overview.
Yeah, that's you get to focus on the high level concept, and then you get to hide those unnecessary details. That's exactly right. That helps you go ahead and not have to worry about the internal workings of our system, where we can then start to bloat it up. Like we abstract it away so we know instantly what are the inputs and outputs. Like think about some of the ways that, so let me think about this. In any of your classes, when you were doing, everyone did JUnit testing, right? How did they teach JUnit testing? Did you write your test first and then do your implementation? Oh, well, in test-driven, so there's two different ways that you can develop. You could do test-driven development, or you can do development-driven testing, where you build out your application and then you test it to validate and verify it. Typically, the way we're going to look at building our code base is going to be the opposite, test-driven development. Because think of it this way, in test-driven development, you make the test first, and that defines your feature scope, right? So as long as you know what functions or methods are inside of your object or your module, your package, and you know what input you're going to get and the output, then that is what drives you next as a developer to know how and what to implement. And you don't implement outside of that. So you can see how that definitely helps. That kind of idea of abstraction helps prevent any feature creep because you're not implementing anything outside of what you've defined in that kind of abstract set of criteria. How does abstraction help with technical debt? And then you can lean on the concepts from your object-oriented development and from Java 1, Java 2, or what other classes you've had, whether it's mobile apps or web dev or whatever. Yeah, absolutely. Yeah, this idea of abstraction where you can hide the inner mechanisms allow you to exploit things like inheritance. Probably the first thing you noticed using inheritance using an abstract model is it allowed you to define a set of things, and instead of repeating a lot of implementation across multiple classes, classes could just inherit from some abstract class, from some base class, and then that removed the technical debt of you having to repeatedly or violate what we call dry principles, right? Where you try not to repeat yourself. So like, what was was it in Java? It's Java 1 where you first learned how to use abstraction, right? How to use inheritance. Do you remember what the sample was? This in Java 1, was that an employee class or something? Did everyone do the employee class? Or animals? Yeah. But the concept's the same. Probably did y'all stagger the implementation of that where you start by implementing like 3 different employees fully, and then you show how you can remove the kind of novice way of doing it so that all of the related code could go into a base class. And now if we had to change our model of employee, we do it in the abstract in the base class, and it gets fed to all the kind of classes that inherit from it. And then finally, you can see why that can also enhance maintainability for very similar rationales. Okay, well, let's talk about modularity. Why do you suppose modularity is going to avoid our scope creep? Yep. Yeah, so you know exactly where your boundaries are at. And so how does that avoid technical debt then? Exactly, yeah. And you're not even going to think about things that go outside of the particular the module or the package that you're working on. So if you get like some insight, you're like, well, that might be something cool, but it's not part of the project. That's part of the deliverable that I'm working on. And then in terms of maintainability, how does that help with maintainability? You know exactly where it goes. Yeah, if everything has a place where it lives at, and you have identified where these places go, the moment something breaks, then you know exactly where in your large landscape of code to drill down to look for that problem. Okay, let's talk about the separation of concerns. How might this avoid some scope creep? And you can see some of these concepts kind of overlap with one another, right? So separation of concerns is just being able to, so if we're building modules and we're creating modularities, the role of separation of concerns has inside of this, because notice when we're talking about CLAMS, these are all concepts that interrelate. So there's some overlap in concept, but this particular part of it relates to how do we discretize? How do we define what the boundary point is? Because we're the human designers, so we have to decide, does this get included in this module or this other module? And so you do that by defining what are the concerns and separating your modules by the concerns that they have. So they all play into, so clearly we're talking about modularity, but what defines the modularity is your separation of concerns. And then once we have our separation of concerns, then we can talk about loosely coupling them so that they're as decoupled as possible. Again, that goes into the concept that goes into that, and that also talks about like what is cohesion. Cohesion, separation of concerns, kind of talk about two different things that are related, like two sides of the same coin. Because if you have a separation of concerns on how you define different modules, cohesiveness is what goes internal to a module. So if one's talking about what belongs, the other talks about how they group together into a set. So you think of it as like interset rules and element rules. If we're trying to like define or build our application using set theory concepts, as an application is a component, as a set of components that interwork together, or modules. And then finally, how do you suppose structured framework? Structured framework is where we can talk about designing our process based off of deliverables and milestones and all of these other things. How might structuring our implementation, our dev cycle, might avoid things like scope creep? Exactly. Yeah, you're deskeratizing. If you were to linearize, if you were to map your dev time onto like a line, you can create a deskeratization, like points, like ticks on that, where you can validate and verify what's supposed to happen. And so now this allows you to measure the dev cycle in addition to the code you're implementing on. And again, we can see how that could avoid technical debt because it allows you to catch things more rapidly. And when you catch something rapidly, it prevents you from having to refactor things in the future. And then obviously also maintainability. I think these are kind of self-obvious at this point. So I'm just going to run through. So let's talk about then, if these are the driving principles on how we go ahead and build out our software in a more engineering approach, as opposed to just kind of a developer approach, what are the essential tools to drive us towards where we need to get to? So it's going to be, and I'm going to line list these. And if you have a question, ask me, because I think some of these are kind of self-obvious. Testability. It's important that you design with testability in mind. It's important that you design with deployability in mind. Speed. You want to fail fast and iterate quick. And then that allows you to go back and do that experimentation, get that feedback, and then refactor if you need to. Controlling the variables. So when you're working in a large system, just like in science, you want to have a minimal amount of variables inside the system so you know what works and what doesn't work. So when you're testing something doesn't work, you can isolate it quickly. And then continuous delivery. This means as you keep delivering on these iterative versions of your software, you want this, you want to constantly be doing this. You don't want to just have it staggered or staged. You're going to constantly be expanding on your system. So you need to develop a pipeline that allows for that. You need to develop a approach that allows for you to constantly be delivering additions to your application. This isn't just one of the big things about software engineering is an approach that isn't just intended to launch a piece of software and like kick it out the door and never look at it again, right? The continuous delivery is that you want to maintain it. You need to patch it. You need to update it. You need to give new features or security updates. So you want to know what that pipeline is going to be for the entire life cycle. And a big part of that life cycle, probably the longest part of that life cycle, ideally, is going to be in your maintainability stage. Okay, so let's redefine how most people usually think about software engineering. So here, we want to think of software engineering is about creating stuff that works. At the end of the day, that's the goal. Like when we talk about engineering, we're talking about stuff that works. What do engineers do? The reason why engineering is so practical and demanded in society is because they build bridges, right? They build buildings. They build things that people use. So let's talk about some of the misconceptions once we apply software in front of the term engineer. It can mean one of two things to a lot of people. Either it just gets mistakenly equated towards just coding, where software development and software engineering are kind of like just an analog to one another, or it could be thought of as just something that's overly bureaucratic, something that produces a lot of policies, a lot of rules that doesn't seem like it's necessary for you to actually get a working application. So both these misconceptions can lead to inefficient practices and poor outcomes, because it's a misunderstanding of what the idea, what the goal, what the motivation of software engineering is. So in true engineering, engineering should be about applying the right practices and principles to achieve the best possible outcomes, not about rigidly following outdated procedures for their own sake, right? So if you have rules, how often is it the case that you might see someone hear a rule in software development, something that governs the design of software, and they'll actually create more brittle software in order to put that rule in place? That's a misuse of the rule. That's not what the rules are there for. So there are times where you don't have to follow the rules, because what it's more about is using the right rule when it makes sense. Maybe there are times where using a functional paradigm versus a procedural paradigm versus an object-oriented paradigm makes sense. And so use the right approach for when it makes sense. Okay, with that said, let's look at some of these guiding concepts that will allow you to decide how to do this interplay. So first of all, you have to have these agreed principles. These agreed principles might be, for instance, these foundational guidelines in CLAMS that we talked about, or best practices like code reviews, testing standards, or continuous integrations. These help guide our development and ensures that there's consistency, reliability, and maintainability across the project, across all team members, right? It's important that everyone's on the same page when you're delivering across one single application. To put this as an analog to something that's not software, to give you a visual of this, imagine if you're all animators for a Disney movie. Wouldn't it be important that everyone adheres to the same style? Wouldn't it be jarring if between each frame, the character designs was rapidly and like ridiculously different based off of what each pod decided to do? And so that's why you have to have a shared standard between everyone, so that when you look at the entire production as a whole, it's consistent, it's cohesive. Okay, however, there are instances where we want to avoid dogma. So while the principles here are essential for maintaining the quality and consistency, being overly rigid can stifle innovation, adaptation, or adaptation. Since adherence to principles can sometimes create overhead, there's a technical overhead actually adhering to principles, right? So like, sure, you should be highly decoupled, and you should be modular, and you should follow all the rules of CLAMS. But when you're in the experimentation phase, when you're looking to fail fast, when you're trying to see if something even works, you can ignore those rules, because that's not what you intend to deploy. That's not what you intend to share. You're trying to see if something works. Once you know it works, then you can start adhering to the appropriate rules. But don't start implementing your code necessarily just to adhere to the rules. First, start to make sure you understand what the problem is and that you have a solution. Then you can take that solution and start adhering it to the rules. That's probably one of the most obvious examples of when to and not to follow these guidelines. Now, and then of course, the trick here is that balance between having discipline and flexibility. And that comes with practice, right? That comes by doing. And of course, this is just reiterating really about how we harness that scientific reasoning for better software. What we do is as a software development, as you're iteratively building out your software, remember, I said this is a cyclical thing. So we talked so far about doing this through like a single cycle, but then when we cycle over again and we keep adding more and more functionality, one thing you should do is take that scientific method approach challenge the assumptions that were made prior and see if they still hold as we add new functionality, new features, or expand. Don't just assume what was there before can be the same way throughout the entire life cycle of your application. You might have to reiterate, you might have to refactor as complexity is introduced. So be prepared for that. As you're expanding on what you're working on, be prepared to challenge assumptions that were made previously. Nothing should be treated as a solved problem. It's always open up for a new theory to make it better, to make it more expressive, to make it more abstract or generalizable. Just the goal is to make it a model that works. And of course, we can challenge assumptions by refining through experimentation. So as you're adding complexity, experiment, see what breaks, what doesn't break, how robust your original solutions are. And then you're going to decide whether you have to make changes or if you found a better approach through data-driven decisions. So based off of the results from your experimentation allows you to know whether you have to refactor or not, or how to expand. And again, this is just kind of giving you an idea of how to step through and be a software engineer as you start to develop your code base. Okay, does anyone have any questions about the processes? So this is kind of like trying to map software engineering as it would to a scientific method and a more traditional engineering approach. Does this so far make sense? That's what I thought, like chapter 1's a textbook. And this is a really good textbook, by the way, so I definitely encourage you to read through it. Okay, so let me pivot briefly and motivate a historical rationale for software engineering. It's sometimes good to know where the people before us came from and why we're at the current state that we're at right now. So let's talk about the birth of software engineering. It was actually done by a woman software engineer, the name of Margaret Hamilton, who had coined the term software engineering. She led the development of the Apollo's flight control software. And she emphasized the need for reliability and systematic approaches in critical systems. And so this led towards having a NATO conference in 1968. This was the first conference on software engineering that was held in response to what we'll call a software crisis in the 1960s. And so the software crisis was a recognition of the challenges in building reliable, maintainable software systems in order to grow complexity. We're going to talk more about that in the next slide. I don't want to delve too much on the NATO or the software crisis on this slide. But really, the significance here is this allowed us to develop a foundation for the discipline of software engineering. There was a recognition that software, that engineering software was a non-trivial task. But we're going to see how it's different than hardware engineering. And so, obviously, the legacy from even all the way back then, 1968, is that the principles and practice established there during that time period continues to influence how we develop software to this day. Okay, let's understand a little bit about what the software crisis in the 60s was, right? Because right back then, it doesn't sound like there wasn't nearly as much computational equipment. But the computational equipment that was there was owned by really big industries like governments and big financial institutions. So here, what they found is that there was a complexity of programs. By the late 60s, software has become complex enough to challenging to develop and maintain. What's the implications of that? We're going to see in just a moment. And so then there's finally this understanding that there's a separation between hardware and software. You have to understand back then, the software was so highly integrated into the hardware that there wasn't a clear distinction between the two. I mean, you would program, you would give instructions to the hardware, but this is where the idea of creating complex software systems started to mature into a concept in and of itself. If you think about computer science now, computer science is divorced from electrical engineering. At that time, highly coupled. There's been a decoupling since then. Okay, so what does it mean to have a software crisis that actually calls for software engineering to even become a thing, which is still a thing? Like, these are still some of the things we're trying to control. So you have increased complexity of software systems. As computer hardware became more powerful and capable, software systems grew increasingly complex. The complexity made it difficult to manage software projects, which led to frequent delays, cost overruns, and failures to meet specifications. So the development of large-scale systems, like the ones used in aerospace. Think about what the 60s were. What happened in the 60s? Significantly. 69 in particular. Yeah. I mean, you want to have some really robust software when you're talking about taking a rocket and putting it into orbit with humans on it, or just with anything on it. And so these are the software systems that were developed by aerospace and defense and business that they quickly realized that a majority of these applications for these larger systems would fail. Why? There was a high failure rate for a number of reasons. Systems were often either delivered late, or they ran over budget, or they failed to meet the required functionality. And this became very problematic for critical systems, like ones that would work on rocket ships. And the rationale behind this is back then, there wasn't a standardized practice and methodology. So you could clearly see if each person is doing their own thing, and these things are radically different, how that can lead to issues where either you have to have high technical debt where you're refactoring, or you have unforeseen issues that then cause collisions or bugs. And back then, if you had a bug, it could literally destroy your hardware. And then you have to remake your hardware, which would run your budget up. I mean, back then, system crashes could literally like crash the system. There wasn't just rebooting. And then finally, there was even back then a growing dependence on software. Even in the 60s, different points. I was watching a Columbo episode the other day, and there was a this was like in the 80s. This was I think one of the episodes in the 80s, maybe the late 80s. There was traffic cameras in that episode. It just showed you, and clearly you can see how that projected out. I think Columbo is like set in California, so it just shows you there's a standard that's set and then just expands and then grows out. But shows you even back then, there was still a dependency on software that I didn't even know existed when I was a kid, when I was very young, right? Like I thought that was a newer thing that happened in the 2000s. Anyway, so let's go back to the NATO conference in 1968. So here it convened to address these challenges that was recognized in the software crisis. I mean, this is such a significant software crisis. You can actually read about it. I think there's even a Wikipedia article on it. It's that significant, and that's why we have software engineering as a practice. And so that conference, that NATO conference, became the first conference for software engineering. And you have a lot of very important critical pioneers for computer science that were as a part of the conference. I decided to select this quote in particular from Dijkstra, who I think, if you've ever read any of Dijkstra's papers, awesome computer scientist. He had said the major cause, I kind of like how he has kind of a humor about the way he writes things. So the major cause of the software crisis is that machines have become several orders of magnitude more powerful. To put it quite bluntly, as long as there are no machines, programming was no problem at all. When we had a few weak computers, programming was a mild problem. And now that we have gigantic computers, programming has become an equally gigantic problem. This was in the 60s. Okay, so let's talk about now. So there was the understanding then that you have to decouple this concept of hardware versus software reliability, or advances even. So the idea is that with hardware advances, you can make tremendous strides on what you can do with these machines, with what you can build out. Achieving exponential results in performance and cost efficiency. Because with Moore's law, if you can compute more things, you can do things quicker and it brings the cost down, right? So hardware comes down very rapidly. The ability to produce and maximize the output of code becomes much quicker, so you have less of a lag time. So the idea back then was Moore's law is like, yeah, the hardware, computational hardware, we can solve problems by just adding more transistors onto our chips. And then we get faster results, right? And so those same laws don't apply to software. In fact, it's like an inverse relationship. The more processing power you have, it seems like the more people you have to bring to the table. Well, what it is software development isn't strictly a hardware problem. It can't be solved by adding more transistors to the problem. And that's because there's two things that make software progress slower. Unlike hardware, software must be tailored to specific needs, requiring a more iterative and experimental approach. And also there's a human factor there that you don't have with hardware as it runs on itself. Software development is heavily influenced by humans and team dynamics and decision-making processes and communications, which can slow the progress for how the software can, for building out larger software systems. So when you're building out larger hardware systems, this makes sense. Software systems do not follow the same rules. This was something that was, I think, identified in Brooks in his paper, There's No Silver Bullet. I want to say this was in 1986. Silver bullet being there's no silver bullet for software development, like there is for, I guess, Moore's Law with hardware. And so what are the implications of this? You have to understand the reasons behind your slower software progress. You have to dissect and understand why your software progress is slow. Even if you have the fastest hardware, it could be team dynamics. It can be poor programming choices. It could be poor modularity, right? You have to do a dissection and identify what it is, and then focus on methodology. And that's why, to this day, software engineering, many decades later, is still a methodology-based concept, right? It's like, how do we organize these things so that we can deliver, and how do we take concepts to break complexity down into something simpler? And so this led to a paradigm shift. I'm sure everyone's familiar with the term paradigm shift. If you're not, a paradigm shift just really kind of occurs when you have a dominant framework or assumption in a field and you can replace it with a new model that better explains or addresses the issues at hand. So for instance, we used to have a geocentric understanding of the universe. And when we pivoted to a heliocentric understanding of the universe, one that's sun-focused, all of a sudden we had better models that gave us significant advances in our scientific model. So here, we used to have these old paradigms with traditional software, which often was focused on rigid processes, limited flexibility, and narrow focus on coding practices. It followed traditional engineering practices of the day. And so this had to change with the new paradigm where we treat software development as a discipline based off of scientific principles, where there's this discoverability, and there's an experimentation, and there's a feedback, and there's an adaptation towards that. So we don't want to have these hard, narrow views from the get-go, because that if things change over the course of building out the application, that's going to really prohibit us. It's going to screw us over. And of course, we have our rigid processes. This just talks about like following things like the waterfall approach. We'll talk about that later. Limited flexibility. This means that we can't cope well with things that change as we start to mature our software and develop it. And narrow focuses on practices. This is where we focus more on just getting code that produces the output we'd expect without doing it in a way that considers maintainability and scalability and other concerns, when we only focus on one achievement and not like what the secondary consequences of those are going to be. And so by adhering to these engineering approaches that we've defined earlier, that's going to give us our quality and effectiveness, our efficiency, and our sustainability inside of the software that we deliver. So giving us a much more kind of engineered approach than what just a developer would do without defining a set of principles and practices and methodologies for designing software and delivering it towards team members. So one thing to have in mind, we've already talked about this, is you want to be open for continuous evolution. You want to you understand that in the maintainability phase. So let's talk about maintainability phase. You want to understand that, you know, as you continue to build software out, sometimes there'll be outdated practices. Start to evolve beyond that. Avoid inefficient processes. You'll learn what inefficient processes are by doing things. As you notice how things don't work well, evolve. Find what's inefficient and become more efficient. You know, you have legacy tools and technologies. Learn to, like, you'll have to refactor over the course of your career. You'll have to update your code base and not rely on things that have gone delinquent. And you'll have to sometimes have a mindset and culture that you want to also be evolutionary. You don't want to be inside of a place, an organization that just kind of culturally does things as they've always been done before. You want to evolve across every facet of kind of the application development environment. Okay, let's see. And that's pretty much it for chapter 1. Is there any questions? I feel like this was really kind of self-evident, but what it allowed us to do is kind of articulate in precise terms exactly what software engineering is historically and how it relates to engineering, but also how it doesn't relate to engineering. How engineering can use something like a waterfall approach, but we're going to use an agile approach in software engineering. Yes, I'm going to put these inside the Discord as well, inside a resource section, as well as the videos as well. Any other questions? Okay, there's 2 things I wanted to do. This was the first, took me a little bit longer. The next is I want everyone to break into pods. So let's make pods. What's that? Pods of 3. So we have, and I'm going to okay.